Graphing cube root functions. So we're going to talk about graphing these cube root functions. It's very similar to graphing square root functions in terms of the transformations we're talking about. Cube root function is a radical function with an index of 3. That means if I have the square root symbol or the radical, that little number right here, that is your index. Okay, so when we have a 3 in that position, so it looks like this, that is the cube root function. Okay, and it has to have the independent variable under the cube root symbol. In other words, the independent variable, or x. Okay, so the parent function of a cube root family is f of x equals the cube root of x. And that's the graph that, when looking at these, we judge all of our transformations from. Okay? And so we'll see that in this lesson today. But before we can do that, we need to actually talk about what those transformations are. So just a quick reminder, when you have the function f of x equals a times the cube root of b times x minus h, all plus k, a does a certain thing, so does b, h, and k. If it's outside of the parentheses or outside of the radical, so that would be a and k, those are vertical items. Whereas if it's inside, it's moving things horizontally. And the one way you can think about that, when you move vertically, you're moving on the y-axis. When you move horizontally, you're moving on the x-axis. Okay, these things move on the x, these things move on the y. Okay, or move vertically versus horizontally. Okay, so what does A do? Well, A is a vertical stretch. Remember, if it's a stretch when A is greater than 1, or shrink, and it's a shrink when A is between 0 and 1. If we have a negative A, it could be a reflection over the x-axis. Okay, and that's because it would move vertically. So if I go over the x-axis, let's say it points here and I reflect over it, I'm changing vertically, up and down. Okay. So what does B do? Well, B is inside, and so B deals with a horizontal. Okay, and notice A was multiplying and it was a stretch and shrink. Well, B is multiplying also. So it's a horizontal stretch when B is between 0 and 1. Kind of backwards on it. Well, it's not kind of, it is backwards. So it's stretching when B is between 0 and 1. In other words, like 1/2 or something. Or it's a shrink when B is greater than 1. And we stretch and shrink by the reciprocal amount. So like if B was 1/2, we'd be stretching by a factor of 2. Or if B was 3/4, we'd be stretching by the factor of 4/3. If B is 3, we'd be shrinking by 1/3. If B is 7, we'd be shrinking by 1/7. We take the reciprocal. Okay? If B is negative, it's a reflection over the y-axis. So think, if it's here and I'm going over the y-axis, I'm changing horizontally. Okay? All right, well, what does H do? Well, H is on the inside, so it moves things horizontally. Okay, and we're adding, so it's a horizontal translation. Translation is like a slide. Okay, so if you think of it that way, like a slide. Okay, and if it's minus H, it's going to the right. So that would be your minus H. And if it's plus H, it's going to the left. That would be the plus H. And that's backwards, right? You think like negative usually goes this way on X. Well, it's going this way if it's minus H. And plus H goes this way. Okay, and then the last piece is the k, and that's on the outside, so it's dealing with vertical. And it's adding, so it's a vertical translation. Once again, that's like a slide. Up if it's plus k, or down if it's minus k. All right. And so what I want to do is I actually want to graph the parent function here. Okay, in order to graph the parent function, we need to find one other thing, and it's called the point of inflection. All right, so graphs of cubed roots look like this a lot, okay, or some variation of this. The point of inflection is that point at which the graph turns, okay, or curves. That's our point of inflection. And the way we find the point of inflection, just like we did the vertex when we were dealing with square roots, if you recall that, this point here, the vertex. Well, here with cubed roots, just like with square roots, the point of inflection is determined by hk. So if you identify what h is and what k is, you will know the point of inflection, and that just tells us where to start our graph. Okay, so for instance, in this parent function, the cubed root of x, we're not adding or subtracting anything to x, so h is 0, and we're not adding or subtracting anything outside the radical symbol, so there's nothing out here, so k is also 0, meaning my point of inflection is right here at the origin. It also tells me where I'm going to start my table. Okay, I'm going to put x right here as 0. That's my h value. This is going to be my point of inflection. And you can even test it. The cubed root of, when I put 0 in for x, cubed root of 0 is 0. Okay. Well, the next perfect cube I want to do, if you think of your perfect cubes, like x and x cubed, well, when x is 1, x cubed is 1. So that's a perfect cube. 1 is a perfect cube. So if I put 1 in for x, 1, I take the cubed root of 1, I get 1 out. That gives me 1, 1. Okay. Well, if x is 2, x cubed, 2 times 2 times 2 is 8. So the cubed root of 8 would be 2. So we want to use our perfect, just like we use perfect squares when we're doing squares, we want to use perfect 0, 1, and 8. Well, that means I'd have to put 8 in for x to get 8 here. And the cubed root of 8, the output would be 2, because 2 to the third is 8. All right, so that would be at 8, 2. So I'm trying to make these perfect cubes. Another thing to keep in mind with cubed roots is you could take cubed roots of negatives, right? Because a negative times a negative times a negative is a negative. Okay? So we're saying what number times itself 3 times makes negative 1? Well, that would be negative 1. So when I put negative 1 in for x, I get negative 1 out. And that would also mean that the next perfect cube would be the cubed root of negative 8. So when I input negative 8, I get, well, negative 2 times negative 2 is 4 times negative 2 is negative 8. So, oops, that would be negative 2. So when I input negative 8 in, the cubed root of negative 8 is negative 2. All right. And so you have this function, oops, the graph of this, that does something like that. There is my cubed root function. That is the parent function. Now from that function, we do all these different things to it. We stretch, shrink, translate, all of that. The key that I want you to, one of the keys I want you to take away here is that you are really using perfect cubes. 8, negative 8, negative 1, 0, 1, and 8. Those are our perfect cubes. And we're inputting those with x because x is right here. So when I input these values in for x, I get these problems. And when I do for these problems, I get these solutions, and those are my outputs. And that gives me the order pair -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. All right. So let's go ahead and take a look at one of these here. Graph each function, describe the domain and range, and compare it to f of x equals cube root of x. Now, I just read those directions that made me remember that I never talked about domain and range. Domain, remember, says where does this exist on the x-axis? For what values of x? Well, notice this graph goes on forever to the right and on forever to the left. That means my domain is all real numbers. Okay? You could abbreviate that as that right there if you like. And where does it exist on the y-axis? Well, it's going up forever, it's going up slowly. It's going down forever, though slowly. So that's also all real numbers. Okay, so the domain and range for cube root graphs is all real numbers. If you want, you could write it like that. Okay, so just remember domain stands with x, range is dealing with the y-axis. Just alphabetical, right? Okay, let's go ahead and try this one here. So the cubed root of x minus 3. So we're going to put that in here. All right, so our point of inflection, well, we need to know what hk is. Okay, so hk, well, in this case, there's nothing inside, so that's h is 0. K is minus 3. So that means my point of inflection is going to be 0, -3. Okay? My domain I already know is all real numbers, and my range is all real numbers because everything's going to exist for my cubed root. So I want to start at my point of inflection, 0. That means I'm inputting 0 for x, and then I'm subtracting 3. The cubed root of 0 is 0, minus 3 is -3. Okay, and that's my point of inflection. And now the next thing I want to do is note that I'm going to only change what's going in the cubed root symbol. I am only replacing x. So I want x to be perfect cubes here. I want this thing inside here to be perfect cubes. Okay? And so I'm going to input the first perfect cube. Remember, my perfect cubes are 1, 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64, and so on. Those are perfect cubes. So I'm going to input 1. It means x is 1. So when x is 1, the cubed root of 1 is 1. 1 minus 3 is -2. Okay, the next perfect cube is 8. So I'm going to input 8 into x. Okay. And I can't get my 8 to start in there. There's 8. So we're going to have to kind of trick it there. That's 8, and the cubed root of 8 is 2. 2 minus 3 is -1. Okay, and I'm now going to put -1 in. The cubed root of -1 is -1. -1 minus 3 is -4. Okay, I'm now going to put -8 in. Cubed root of -8 is -2. -2 minus 3 is -5. And so note, I have 8, -5, or -8, excuse me, -5, -1, -4, 0, -3, I already have, 1, -2, and 8, -1. And so my cube root function looks like that there. Comparison, well, what is happening? Well, this is a vertical. It's happening on the outside. the 3's on the outside and subtracting. So it's a vertical translation down 3. All right. And notice my graph of my parent function is just went down 3 units. So if I wanted to, I could have just started by putting in my parent function. So here, 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 and there, and just moved everything down 3 units. That's all that's happening. That's another way to graph it. All right. Well, let's try another one here. Okay, we now have 3 times cube root of x. All right. So the point of inflection, well, h, oops, sorry about that. hk here. So h is 0. K is 0. We're not adding or subtracting anything to x. We're on the outside. I already know my domain and range. It's always all real numbers with cube roots. And I can look at it and I say, well, what's happening on the outside? This is going to be a vertical stretch because it's multiplying, and it's multiplying by a number bigger than 1, stretch, by a factor of, for now on, we're going to say BAFO, BAFO. So you can call that BAFO, by a factor of, it's quicker to write out, 3. Okay? So I'm going to start at my point of inflection, 0. I have 3 times the cubed root of, I'm inputting 0. The cubed root of 0 is 0, times 3 is 0. Okay? So really, all I'm doing in this whole thing here is replacing the x with perfect cubes. So once again, and I keep making a big deal about this, I am just replacing x with those perfect cubes. Which perfect cubes? Well, I'm talking about these ones over here, right? In fact, 0 is my first one. Okay? So I put in 0. I put in 1. Okay? Well, x is 1. The cubed root of 1 is 1 times 3 is 3. I put in the next perfect cube. I'm going to make x equal 8. So 8 goes in for x. That gives me 8 here. The cubed root of 8 is 2 times 3 is 6. And the ones I don't have listed over here, I guess I'd be negative 1, negative 8, negative 27, and so on, right? Those are also perfect cubes. Okay? So I'm going to put in negative 1. Input that. Cubed root of negative 1 is negative 1 times 3 is negative 3. And I'm going to input negative 8. So that puts negative 8 right there. The cubed root of negative 8 is negative 2 times 3 is negative 6. So that gives me negative 8, negative 6, negative 1, negative 3, 0, 0, 1, 3, and 8, 6. So this graph looks like that there. It's a vertical stretch by a factor of 3. Now note what the parent function looks like. The parent function would be here, here, and here. Oops, here. Okay, and then here, and there. Well, note, when I say a vertical stretch by a factor of 3, we're stretching away from, just so we understand what we're looking at here, we're stretching away from this axis right here. And so really what you're looking for is you're looking at this distance right here. So this distance right here is 1, whereas this distance from here down to there is 3. That's 3 times as far. This distance is 2. Whereas this distance is 3 times 2, or 6. 6 times as far. So that's what you're doing. You're doing that vertical stretch by a factor of Okay, you're stretching away from that axis there. So these distances are getting greater, just so you know. All right. Well, let's go and try another one here. This is kind of the more difficult one. I have the cubed root. Let's switch my colors around here. I have the cubed root of x minus 2. So first, point of inflection. Well, I have a minus 2 in there. So when I'm looking at hk, that negative 2 is my h, except for, remember, it's x minus h, so it's always opposite of what you see. So it's positive 2, and a lot of students will make that mistake I just did there. And then we're not adding anything to the outside. Okay, so we get 2, 0. So remember, it's always opposite of what you see here. And we know that because my graph that starts here, this is a horizontal translation. Remember, it says minus, it's going to the right 2. So it's going to start right there at 2, 0. It's moving to the right. Okay, this is a horizontal translation. Right 2. The domain I know is all real. The range is all real. Okay, and so I start here when x is 2. It's my point of inflection. So I have the cubed root of, well, that becomes 2 minus 2 in there, which, by the way, is 0. So let me show this kind of like so. We'll put two things there. 2 minus 2. So the thing I'm putting in for x is right here. Oops, let's switch up that color there. Let's erase that. Okay. So I'm replacing x with that 2. We get 2 minus 2, which gives me the cubed root of 0. And the cubed root of 0 is 0. Okay? And so each of these, I'm doing that. I'm replacing x, and I'm subtracting 2. I'm replacing x, and I'm subtracting 2. I'm replacing x, and I'm subtracting 2. And what I'm trying to get on each of those, I'm trying to get my perfect cubes. 1, 8, negative 1, and my negative 8, right? And so you've got to ask yourself, what can I put in right here for x in each of these to get those values? So you could either do the math or you could do guess and check. You say, okay, what minus 2 is negative 8? Well, negative 6 minus 2. So I'd have to input negative 6. That would give me root negative 8, which would give me an output of negative 2. What minus 2 is negative 1? Well, that would be 3. So I'd have to input 3. Oops, I'm sorry, it wouldn't be 3. Okay, it would be 1 there. Okay, sorry about that. And so I'd have to input 1, and the cubed root of negative 1 is negative 1. And so if you're like, man, I have a hard time doing that in my head, then you could just do the math right over here, right? You're saying x minus 2. You want x minus 2 to equal negative 1. You want this to become this. So you just do that math. Well, add 2 to both sides. So x would have to be 1. So if you wanted to do that here, you could say, okay, what minus 2 gives me 1? So I want this, x minus 2, to equal 1. Well, add 2 over, and I get x would have to be 3. Okay, so that would put a 3 there, and 3 minus 2 is 1, cubed root of 1 is 1. Okay, what minus 2 is 8? This would have to be 10. Okay, and so you have to go with 10 here, and 10 minus 2 is 8, cubed root of 8 is 2. And so we get negative 6, negative 2, 1, negative 1, 2, 0, 3, 1, and 10, 2. And there it is. It's moved our original graph 2 units to the right. So our original graph started right here, and it went that way too. That way too. This point that was right there is that way too. Everything is moved to the right 2 units. Same thing here. And here. Okay. Well, let's go ahead and try another one here. 1/3 the cubed root of 1/3 x. Okay. Point of inflection, well, that's our HK. So we get 0, 0. Okay, so we start here. That means POI right here. 0, the cubed root of 1/3 times x, which is 0. Oops. Which would give me the cubed root of 0, which we know is 0, 0, 0, 0. Okay, so once again here, if I'm looking at this, I'm saying the cubed root of 1/3 times x. So times what gives me the cubed root of 0? Okay, the cubed root of 1/3 times what gives me the cubed root of 1? The cubed root of 1/3 times what gives me the cubed root of perfect cubes, 8. So trying to make those same perfect cubes. All right, and so kind of looking at that, x is being replaced with numbers that are going to give me these perfect cubes here. Right? So if you wanted to, if you're not sure, just do the math off to the side. You want 1/3 of x, 1/3 times x, to equal -8. So what would x have to be? Well, you'd multiply both sides by 3. X would have to be -24. So I put -24 in. Well, 1/3 of -24 is -8. And that gives me -2. Now, obviously, you can't graph -24, -2 on this graph. So that will be a point we'll just have to ignore on this one. But you can keep doing that, right? You can say, okay, well, 1/3 times, I know the fraction gets intimidating, but 1/3 times what is, well, we want to make -1 now. I'll multiply both sides by 3, so x is -3. Right? So -3, if I put that in for x, I get the cubed root of -1, and the cubed root of -1 is -1. Once again, 1/3 times x equals, well, we want to make 1 now. So x would have to be, multiply both sides by 3, x would have to be 3. So again, here, 1/3 is 1, and the cubed root of 1 is 1. Then 1/3 times what equals 8? Well, you have to multiply by 3, so you get x is 24. You put 24 here, and you don't switch slides like I did. Okay, and you put 24 here. 1/3 of 24 is 8, and the cubed root of 8 is 2. Okay, so we can't graph this one nor this one because of the 24s, but we can go -3, -1, and then +3, +1. So this graph is like really ultra skinny, just kicking back, laying down there. Okay, so there you got it. Domain still is all real numbers. I keep switching slides there. Range is still all real numbers. And the comparison, well, 1/3 on the inside. So that's a horizontal. And it's between 0 and 1, so that's a stretch. And it's a stretch by a factor of, well, we take the reciprocal. The reciprocal of 1/3 is 3. So it's stretching away from the y-axis this time, 3 times. So usually it's right here. which is 1 unit away from the y-axis. Well, this new point is 3 units away. Okay? So it's a horizontal stretch by a factor of 3. All right. We have a couple more graphs. We're dealing with opposite roots here, and I'm just going to kind of go through these fairly fast here. Okay, point of inflection, HK, is 0, 0. Range over. And the negative's on the outside, so remember that is a vertical reflection. Now usually your textbook won't have you put vertical, they'll just say reflection. And so that's okay if you ignore that vertical and just say it's a reflection over. Okay, it's on the outside, so it's over the x-axis. Okay, so we have the negative cubed root of x. We're starting at 0, 0. That's our point of inflection. Okay, that gives me the negative cubed root of 0, which is 0. And then I'm going to put it, I want to make 1, which means x has to be 1. Cube root of 1 is 1 times negative 1 is negative 1. And I want to then make x 8. And the cubed root of 8 is supposed to be the negative cubed root in here. All right, that negative sign just wants to disappear, so I'm going to move this here. Okay, cubed root of 8 is 2. That makes that negative 2. Make this the cubed root of negative 1. So x is going to be negative 1. That gives me negative 1 times negative 1, which is positive 1. And then cubed root of, well, we're going to put negative 8 in. We have that negative on the outside. So the cubed root of negative 8 is negative 2 times that negative gives me a positive 2. So notice we get negative 8, positive 2, negative 1, positive 1, 0, 0, 1, negative 1, and 8, negative 2. So this graph from our parent function has just flipped over the x-axis. So there's that graph. That's a reflection of our original graph here. This point went up, this point went up, that one went down, that one went down. So our parent function has become that. Whereas this one right here, this next one, the point of inflection is still 0, 0. So we still start right here. We have POI here of 0 with a cubed root of negative x. So that means when I put that 0 in, I have a cubed root of negative 0, which is still just 0. No such thing as negative 0. Okay. But when I put the 1 in, now for x, I get the cubed root of negative 1. Oops. And the cubed root of negative 1 is negative 1. And when I put my 8 in, well, that gives me the cubed root of negative 8, which is negative 2. I have my negative 8, so when I put my negative 8 in, the cubed root of negative 8 is negative 2. Well, actually, I'm sorry. Negative 8 times negative 1 is 8, and the cubed root of 8 is 2. And I should have actually put 1 in there, getting a little ahead of myself. So the cubed root of negative 1 is negative 1 times negative 1 is 1, and the cubed root of 1 is 1. Put negative 8 in. Negative 8 times negative 1 is 8, and the cubed root of 8 is 2. Okay, and so I have negative 8, 2. I have negative 1, 1, 1, negative 1, and 8, negative 2. All right. Now something's interesting here, because those two graphs look identical. Domain and range are the same. However, the comparison, this is a reflection over, since it happened on the inside, it's over the y-axis. A reflection over the x-axis, which takes a point that was here and moves it here, and a reflection over the y-axis takes a point there and moves it there. those look the same in this type of graph. Kind of interesting. Right. Okay, well, graph here. Okay, we have a bunch of things happening. So let's look at the point of inflection, our HK value. Okay, H is -1. It's the opposite of what we see in here, right? So it's -1. K is +3. Okay, so we have 2 times the cubed root of x plus 1, all plus 3. Okay, so we have our -1. And I know if I put all this math in right here, I'm trying to make a cubed root become 0 right here, plus 3. Okay, well, when I put -1 in, -1 plus 1 is 0. Okay, times 2 is 0, plus 3 is 3. So -1, +3. Domain and range. Well, that 1, that is a horizontal. So this is the +1. This is what the +1 is doing. Horizontal translation. At 1. Okay? And this +3, which is the very last thing, you should always start with your horizontal translation, as always end with your vertical translations. That's a vertical translation up 3. So notice my vertex usually starts there, or my point of inflection, but it's went left 1 and up 3. Okay, so we took care of those. All right, so from there, what we need to do is we need to go 2 times cubed root plus 3. 2 times cubed root plus 3. 2 times cubed root plus 3. And 2 times cubed root plus 3. And what are we trying to make? Now remember, we want our cubed root here to be 1. So you need to say what plus 1 gives you 1. So x plus 1 we want to equal 1. So what does x have to be? Well, subtract 1, x would have to equal 0. So when I put 0 in, 0 plus 1 is 1. Cubed root of 1 is 1. Times 2 is 2. Plus 3 is 5. Okay? Then I want to make 8. So I need to think to myself, what plus 1 will give me 8? So x plus 1 has to equal 8. So subtract 1 over, x would have to be 7. If I put 7 in, 7 plus 1 is 8. Cubed root of 8 is 2. Times 2 is 4. Plus 3 is 7. All right. And so we can do the same thing here. We say, okay, what plus 1? What are we trying to make this time? We're trying to make -1. So add that 1 or subtract that 1 over, x would have to be -2. So -2 plus 1 is -1. Cubed root of -1 is -1. Times 2 is -2. Plus 3 is 1. And the last one, I'm trying to make -8. So what plus 1 equals -8? Well, subtract 1 over, I get x is equal to -9. So I put -9 in. -9 plus 1 is -8. Cubed root of -8 is -2. Times 2 is -4. Plus 3 is -1. So my graph is -9, -1. So -9, -1. -2, 1. -2, +1. -1, 3 I've got. 0, 5. So 0 and 5. And 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. So my point of inflection was that -1, 3. So from here, I loop up. Here, I go down. My graph, that last curve was kind of ugly there. My graph looks something like that. What did the 2 do? Well, that was the times 2 was a outside, so vertical stretch, Bapho 2. So 3 different things happen there. And there's the graph. All right, so notice I stretched it vertically, so this graph got a little wider. Okay. Change. Remember, when we're dealing with that, we're thinking slope. This is very similar to what we did with square roots. So find and compare the average rate of change for model A to the average rate of change for model B. Okay. So A to B from x equaling 2 to x equaling 20. So really what all you're doing is you're looking when x is 2, that's that point. When x is 20, that's that point. So you want to find the slope of the line that would go through those 2 points. So you're using the slope formula, y2 minus y1 over x2 minus x1. Or if you wanted on a graph, you could just figure out your rise and run. You have a picture here. You can't do that for model B, though. You have to use this formula. And I'm going to go ahead and use this formula for both of them. Okay, so this is going to be my x1, y1. This is going to be my x2, y2. So rate of change is just slope. Okay, so that's going to be replaced. I'm going to have 20 minus 1 and, excuse me, I actually used the wrong value there. That would be 6, y2 minus 1, y1. And then x2 is 20 minus x1, which is 2. So I get 5 over 18. All right. Well, let's look at the slope for model B. That would mean I'd have to do f of 2, which means I substitute 2 in for x. Okay, and so I'd have to actually do the math there where I say the cube root of 2 times 3. Now the cube root of 3 is approximately 3.7 and 8. Okay, so we get the ordered pair 2, 3.78. All right, that's one ordered pair. And now let's do f of 20. Which would give me 3 times the cube root of 20. Which means I'd actually have to do the math again, where I said, well, the cube root of 20 times 3, and that gives me 8.14. If we round to the nearest hundredth, then this would be approximately. So we get the order pair 20, 8.14. Okay, so here's x1, y1, and x2, y2. And so using our formula, y2 minus y1 over x2 minus x1, we end up with, well, y2 is 8.14 minus 3.78 over 20 minus 2. So notice our denominators in both of them are 18 because you're doing 20 minus 2 in each of them. 8.14 minus 3.78 is 4.36. And really, to compare these slopes, we should really round both of them. Okay, or at least get a decimal. So we'll go to the nearest 10th. 4.36 divided by 18 is 0.24. Okay, 5.18, or excuse me, 5 divided by 18, not 5.18, is 0.28. All right, so when we're comparing, well, Model A has the greater rate of change. And you could say 0.28 versus 0.24. There you have now compared. All right. I think that's all I got for you. Good luck.